This section explains field quantization, the single move that turns a field into particles. A field is an infinite bank of harmonic oscillators, one for every Fourier mode. Quantization is just promoting each mode's amplitude to an operator obeying the canonical commutator. That one step is the whole idea. Everything particle-like falls out of it. The creation operator, written a dagger, adds one quantum to a mode. The annihilation operator, written A, removes one. A particle is simply an excitation, counted by the occupation number of its mode. Mass, momentum, and statistics are properties of which mode you excited, not of a little ball. Here is the inversion that makes the argument go through, and the reason the book opens here. The field is primary, and particles are derivative. The same commutator that gave you one oscillator's ladder, replicated across a continuum, generates the entire quantum of matter. This section explains what a quantum field is and the single calculus that the whole book runs on. A quantum field is a space-time indexed operator. Quantizing means trading the classical field for an operator obeying fixed commutation or anti-commutation relations. After that trade, everything measurable is a time-ordered vacuum correlator, a Green's function, the vacuum expectation value of a time-ordered product of field operators. Chapter 1 installs the calculus. The whole book then runs on. Wick's theorem mechanically collapses any correlator into sums of pairwise contractions and free propagators, and each term is a Feynman diagram. The lambda phi to the fourth exercises are the minimal instance. A symmetry factor is nothing but the count of automorphisms of the diagram that fix its external legs. Master this, and later gauge calculations are the same move with richer indices. The generative seed is this. A theory equals its correlators, and perturbation theory is just contraction. Counting. This section explains renormalization at the structural level, why counting the legs of a diagram tells you whether an integral blows up before you ever evaluate it. Every loop integral either converges or diverges. And one-dimensional count, the superficial degree of divergence, predicts which before a single integral is evaluated. This count depends only on how many external lines enter the diagram, so counting legs replaces computing the integral. When the superficial degree of divergence is greater than or equal to 0, it flags a divergence that must be absorbed into a counterterm, and the external legs dictate the form that counterterm takes. Here is the chapter's thesis. Renormalizability means these mandated counterterms are finite in kind, and each one already appears in the original Lagrangian. The divergences merely rescale couplings you already had. They never demand new physics. Symmetry sharpens the rule. Gauge invariance admits only counterterms of the same invariant form, which is why the photon acquires no mass, and only the term f mu nu survives. This section explains the superficial degree of divergence. One integer, read off a diagram's outer edges alone, decides whether its loop integral diverges and how violently. That integer is d, and it equals 4 minus b minus 3/2 times f. It is a tally of external legs, never of internal machinery. A non-negative d forces a counterterm. Here is the surprise that makes the whole scheme work. Every counterterm the theory demands has the same form as a term already in the Lagrangian, and gauge invariance deletes the would-be exceptions. That is renormalizability in one stroke. Finitely, many divergence shapes, each reabsorbed by shifting a coupling already there. Power counting is a dimensional oracle. The boundary of a graph predicts the infinity inside it before a single integral is evaluated. This part explains the renormalization group at its structural core, the reason a coupling constant is not really constant at all. A coupling constant is a function of the scale at which you probe, and the renormalization group is the statement that it must be. You introduce an arbitrary reference scale, call it mu, to tame the infinities. No measurable quantity may depend on that arbitrary choice, so whatever explicit mu survives in a prediction has to be cancelled by mu sliding through the couplings themselves. That cancellation is a differential equation, and its solution is the running. The generative move is this: demand invariance under a bookkeeping choice that nothing physical can see, and the parameters are forced to co-vary to protect it. Same interaction, finer resolution, different effective strength. Successive rescalings compose, and that is why it is a group. This section explains how a bookkeeping label that physics is not allowed to notice hardens into a law of motion. That is the whole chapter. Dimensional regularization forces you to introduce an arbitrary mass scale, written mu. No measurable Green's function may depend on where you put it. Demand that independence, and you get a symmetry. Write its infinitesimal generator, and you get the renormalization group equation, the homogeneous form in Chapter 3 that the authors prefer, over Caylanius form. The payoff is that the coupling constants deserve the name only loosely. They run with scale rather than staying fixed. The beta function is the velocity of that flow, and its sign alone decides the theory's fate at short distance. This is the same move as gauge redundancy itself, a freedom in description tightening into a constraint on dynamics. This layer explains how the entire particle spectrum reduces to one idea from group theory. The multiplets of matter are shadows of a group. The chapter makes a single move, identify each family of particles with an irreducible representation of SU3. The group is what the spectrum is, its symmetry constituting the particles rather than being draped over them from outside. Quarks are the defining representation, the smallest faithful one. Every hadron is then a tensor product of quarks, reduced into irreducibles. Mesons come from the 3 tensored with the conjugate 3, written 3. Baryons come from the 3 tensored with the 3 tensored with the 3. Every hadron is then a tensored with the 3. Here is the generative primitive. Hand me a group and its fundamental representation, and the entire particle zoo follows by multiplying and decomposing. Classification collapses into representation theory, and the periodic table of hadrons falls out for free. This section explains why a continuous symmetry collapses to a single piece of linear data. A continuous symmetry is fully carried by its behavior infinitesimally close to the identity. The whole group is recovered by exponentiating that linear data, with u equal to the exponential of I times h, and every structural fact follows from h alone. Being unitary with unit determinant forces h to be traceless and Hermitian. From that single constraint, the chapter reads off everything: the number of parameters, n squared minus 1, the rank, n minus 1, and which representations are real. Here is the step that does the work. This algebra is indifferent to its realization. The same commutators hold. The commutator of Fi with Fj equaling I times Fijk times Fk, whether Fi is a Gell-Mann matrix or a bilinear in quark field operators. So SU3 is the quark model. Isospin, U-spin, and V-spin, raising operators are a change of generator bases inside one fixed algebra. This section explains chiral symmetry, the subject of Chapter 5. Start by giving a fermion no mass. Its 2 helicities stop talking to each other, and the left-handed and right-handed halves rotate independently. one symmetry splits into two, the group SU2 left times SU2 right. Chapter 5 is the toolkit for the consequences of that doubling. Its whole thread is a single mismatch. The Lagrangian carries the full chiral symmetry, but the vacuum keeps only the diagonal isospin part. The vector current stays ordinary and conserved. The axial current is the shadow of the half the vacuum refuses. A broken symmetry cannot stay silent. This is Goldstone's result, so the broken half emits massless quanta, the pions. Every worked problem here, the sigma model, PCA, C, and Goldberger trimon, is one reading of that broken half. This section states the whole of Chapter 5 in a single idea. A Lagrangian can hold a symmetry that its ground state refuses, and every direction in which the vacuum breaks pays for itself with one massless boson. That is the whole chapter. The linear sigma model is its minimal working instance. You write down chiral SU2 times SU2 explicitly, then let it break to isospin, so the pion falls out as the Goldstone mode along the flat directions of the vacuum manifold. The Noether machinery, sections 5.1 through 5.3, is just the tool that lets you read off the current. The near conservation of that current, called PCAC, is the pion's residual mass. The chapter exists to turn the slogan, "Symmetry of the action is not symmetry of the vacuum," into something you compute. The nonlinear model is what survives once the massive radial direction is frozen out. This section explains where a classical symmetry can fail once a theory is quantized. A classical symmetry is a promise the quantum theory need not keep. To compute anything, you must first aim infinities, regulate, then renormalize, and that regulator is a choice. Nothing guarantees it respects every symmetry the Lagrangian wears. Where it cannot, the conservation law fails by a fixed, calculable amount, the anomaly. Fujikawa's path integral, move, in section 6.1 locates that failure exactly. The action stays invariant. The failure lives in the integration measure, whose Jacobian under the axial rotation refuses to equal 1. The chapter carries a single thesis. Renormalization is where symmetry gets tested, and the residue, an anomaly or a radiatively shifted vacuum in section 6.4, is physical, never a bookkeeping artifact. This part explains how a symmetry of the classical theory fares once the theory is quantized and where the answer gets decided. A symmetry of the classical Lagrangian is a conjecture, not a theorem, about the quantum theory, and renormalization is where the verdict is read. The chapter runs that test on 4 fronts and finds 3 fates. The first fate concerns the path integral. The measure need not inherit the action's chiral invariance. That mismatch is the anomaly, Fujikawa's Jacobian, and it is physical. It fixes the rate at which the neutral pion decays into 2 photons. The second fate is soft breaking. A symmetry-breaking term of low enough dimension breaks the symmetry softly, leaving the ultraviolet structure, and therefore renormalizability, untouched. The third fate lives in the vacuum. The vacuum itself can break a symmetry. The Lagrangian keeps, once one-loop corrections reshape the effective potential. Symmetry lives in the quantized theory, never in the Lagrangian alone. This section explains why hard scattering off a proton reveals point-like pieces inside it. Shoot a hard enough photon into a proton and the structure functions forget the scale that produced them. They depend only on the dimensionless ratio x, not on q² separately. That forgetting carries the whole message. A probe that finds no intrinsic length inside the target is a probe scattering off free point-like constituents. Bjorken scaling and the Parton model are one claim. Read two ways: the empirical vanishing of a scale and the structural fact it forces. The composite proton, photographed at high enough resolution, resolves into pieces that behave as if unbound. Hold this primitive. Scale invariance in a response. Function is the fingerprint of point-like structure. The chapter's job is to make that inference rigorous. This section explains what happens when you probe a proton hard enough to see inside it. Probe a proton hard enough and it stops being a proton. The momentum transfer resolves distances shorter than the confining glue can bridge, so what scatters is a single, free, point-like constituent. That is the whole chapter, and each problem is a corollary of it. Cross-sections and sum rules you have no right to compute all collapse into arithmetic over quark charges. Gottfried's 1/3, the electron-positron ratio, the W width, each falls out of counting charges because at short distance the parts stop talking to each other. Scaling is the signature. The structure function forgets its mass scale and keeps only the dimensionless momentum fraction called x. The operator product expansion is the formal engine. It factors the hard, calculable, short-distance coefficient away from the soft matrix element you cannot compute. This section explains how gauge symmetry forces a field into existence. Take a symmetry that already holds everywhere at once, rotating all fields together, and demand that it hold independently at each point. The ordinary derivative breaks. It compares fields at neighboring points that now transform differently, so its difference stops being covariant. The repair is forced rather than chosen. You introduce a field whose own transformation carries exactly the mismatched, inhomogeneous term and cancels it. That compensating field is the gauge field, and the covariant derivative is the only derivative that survives localization. The chapter's whole arc is a single move. Local symmetry manufactures its own connection. Its sharpest instance is general relativity, where the identical construction names the Christoffel symbol. That is gravity read as a gauge theory. This section explains how localizing a symmetry forces a gauge field into being. Take a rigid internal symmetry and localize it, and the ordinary derivative breaks. It subtracts fields living in different frames, and under a point-dependent transformation, u of x, those frames no longer align. Repair demands a connection that transports one frame onto the other before comparing. That connection is the gauge field. Everything downstream is forced, rather than chosen, the covariant derivative's inhomogeneous term, the one carrying the derivative of u, and the field strength read-off from the anti-symmetrized commutator of the covariant derivatives d mu and d nu. Section 8.2 states the surprise flatly. The gauge field is geometry, and F is its curvature. The chapter is one move. Symmetry demanded to hold pointwise cannot be free. It costs exactly one connection whose non-integrability is the force. This section explains why gauge theories force you to break the very symmetry that defines them, and then spend all their effort proving the breaking left no trace. Gauge symmetry is a redundancy. The same physics counted infinitely many times. Quantization cannot integrate over a redundancy directly. The path integral diverges by the volume of gauge. So you break it by hand, fixing the gauge, and you pay with two fictions, an arbitrary parameter called g and unphysical ghost fields. The chapter's entire labor is one proof that neither fiction leaks into observables. That labor is the propagators worked out in every gauge, the states that survive once you impose that the BRST charge, the axial gauge, and the Coulomb gauge, together with the Ward and Takahashi identities and the nilpotent BRST charge. BRST is the residual invariant that guarantees the cancellation. Physical states are its cohomology, the states that survive once you impose that the BRST. The pattern is this. Whenever you fix a redundancy in order to compute, you must separately prove the fixing was invisible. This section explains why a gauge theory carries more structure than its physics needs, and how the physics stays blind to the surplus. A gauge theory is a quotient dressed as a field theory. The connection carries more degrees of freedom than physics does, and the surplus is pure redundancy. You cannot quantize the quotient directly, so you quantize the redundant whole and pay for it. A gauge choice fixes a representative, and every intermediate object inherits the choice. The propagator wears an arbitrary parameter, z. Unphysical polarizations circulate. Faddeev-Popov ghosts appear. The chapter's spine is how physics stays blind to all of it. Ward identities are the first-order accounting. BRST is the exact statement, a global fermionic symmetry with a nilpotent charge, Q where Q squared equals 0, whose cohomology, closed modulo. Exact is exactly the physical Hilbert space. Redundancy quotiented is exactly the physical Hilbert space. This section lays out the structural primitive of quantum chromodynamics. Every number in this chapter is one move, read twice. A color amplitude is the Casimir eigenvalue of a representation of SU3, and any scale dependence is the running of a single coupling. Quarks sit in the fundamental representation, gluons in the adjoint. The trace normalizations and the two quadratic Casimirs, the one of the fundamental and the one of the adjoint, are the only free numbers. The group fixes everything else. What makes quantum chromodynamics computable is the sign of the beta function. The non-abelian coupling weakens towards short distance, so perturbation theory is exact precisely where you probe hard. 3. Jet rates, operator, product expansions, and Wilson coefficients all fall out. The contrast that carries the structure is this. Abelian quantum electrodynamics strengthens at short distance. Flip that one sign, and the entire predictive machinery inverts. This section names the single seed behind every number in the chapter. Every number in this chapter descends from one combinatorial seed, the color factor, the trace, and Casimir eigenvalues of the generators of SU3. Chung and Lee's QCD problems are a demonstration that this single group theoretic input propagates outward. It normalizes the coupling, fixes the quark self-energy, and, decisively, sets the quark self-energy and, decisively, sets the sign of the two-loop beta function, which is asymptotic freedom, the property that makes the theory calculable at short distance at all. The remaining problems, 3 jet cross-sections, the operator product expansion, and the Wilson coefficients, are the harvest. Once short-distance physics factorizes from long-distance physics, the calculable part is exactly what the color combinatorics govern. Here is the chapter's place in the arc. QCD is knowable because its non-abelian arithmetic drives the coupling towards 0. This section explains the structural core of electroweak theory, the single move the whole chapter turns on. Fix 2 things. Fix the gauge group, SU2 sub L crossed with U1 sub Y. Fix the vacuum direction of one scalar doublet. Everything else in the electroweak sector is then forced, not chosen. That forcing is the entire move. Left-handed fermions enter the theory as doublets, right-handed fermions as singlets. Chirality is the input here, not an accident. and the single vacuum expectation value decides what stays massless versus what grows heavy. The photon stays massless because it lies along the unbroken direction. The W and the Z grow heavy because it lies along the unbroken direction. The W and the Z grow heavy because each eats a goal turn. Now, the payoff. For muon masses, the weak mixing angle, even the accidental conservation of B minus L, each of these is the same question asked once more. What does this vacuum leave unbroken? Learn to read the vacuum expectation value, and you regenerate the whole spectrum yourself. This section explains why the whole of Chapter 11 falls out of a single broken symmetry. Everything here comes down to one fact. Chirality is gauged asymmetrically. Left-handed fermions carry weak isospin. Right-handed ones are blind to it. The opening problem, 11.1, makes the seed concrete. In the massless limit, the chiral projection operators 1/2 times 1 minus gamma 5 and 1/2 times 1 plus gamma 5 become helicity eigenstates. So left-handed stops being a formal label and becomes something the weak force can physically select. Every later problem is that one choice, propagating outward, the pion decay constant, F pi, the uniqueness of the Higgs potential, fermion mass matrix diagonalization, and the conservation of B minus L. The unification is not electromagnetism, and the weak force glued together, it is a single SU2 cross U1, whose spontaneous breaking leaves electromagnetism parity, blind, and the weak sector parity, maximal. Both are the residue of one asymmetric gauging. This section explains what electroweak phenomenology does with a theory once it is built. A gauge theory earns its keep the moment its Lagrangian stops being a construction and starts emitting numbers you can weigh against experiment. That is this chapter's whole office. Take the electroweak neutral current, one universal object, vector plus axial, built in earlier chapters, and project it onto whatever external state an experiment prepares. Atomic electrons, a decaying Z, scattering neutrinos, kaons. Every problem is that same move rotated. The surprise that carries the chapter is rigidity. A single parameter, the weak mixing angle, sine squared theta W, fixes atomic parity violation, Z polarization asymmetries, and neutrino cross-sections all at once. One number, many domains. The theory cannot wiggle in one place without committing itself everywhere else. This section explains what electroweak phenomenology actually is at the level of one repeated move. Take the Z boson's neutral current. Each piece of it splits into a vector part and an axial part. You sandwich that current between whatever physical states you can prepare, and you read off the couplings. That single move, iterated, is the whole of the couplings. The point of the chapter is a conversion. It caches Chapter 11's abstract Lagrangian into numbers. A detector actually registers. 3 experiments look different and are structurally one problem. Atomic parity violation, the left-right asymmetry in a Z, decaying to a fermion, antifermion pair, and neutrino scattering. Each one is a bilinear in the vector and axial couplings, and each collapses onto a single knob, the weak mixing angle written as sine squared theta W. The surprise worth carrying is what happens inside a heavy nucleus. There, the axial terms wash out, and only the coherent vector piece survives. It scales with the number of nucleons, and that surviving quantity is the weak charge, written Q weak. What selects a measurable quantity here is coherence, not the strength of the coupling. This section explains why the scattered topics of flavor physics belong together under one idea. Gauge symmetry fixes how forces, couple, but says nothing about why there are three copies of each fermion or why they mix. That residue is flavor dynamics. The electroweak gauge principle acts on weak isospin, blind to flavor. Mass and mixing enter only through the Yukawa couplings to the Higgs, the one part of the standard model that no symmetry constrains. So this chapter's assorted topics, the CKM matrix, the GIM suppression of flavor-changing neutral currents, and CP violation are all readings of that single arbitrary object, the Yukawa matrix. Flavor physics is the study of what the gauge principle leaves undetermined. Each phenomenon here is a projection of the same unfixed structure, which is why they gather as topics rather than as one theorem. This part connects four problems that look completely separate. Technique-quark charges, pseudo-Goldstone counting, Majorana self-conjugacy, and the muon to electron gamma decay all share one move. A proposed extension beyond the standard model is admissible only if it survives the consistency invariance the theory already enforces. Anomaly. Freedom fixes the Technicolor charge assignment. The broken generator count fixes how many pseudo-Goldstones survive. Charge conjugation collapses particle into antiparticle for a Majorana field, killing its vector current. Nothing here is new dynamics. Each one is the existing electroweak machinery, triangle graph traces and symmetry-breaking bookkeeping, turned into a filter on speculative sectors. Consider the chapter's place in the arc. Having built, in Chapter 11, and measured, in Chapter 12, the standard model, you now learn to reject candidate physics beyond it, using only the symmetries you already hold. This section explains grand unification, the structural primitive behind the 14th concept. The starting observation is that the three-gauge couplings are one coupling wearing three masks. Grand unification is the claim that SU3 cross SU2 cross U1 sits inside a single simple group, SU5 and later SO10, broken down to what we observe, with everything else being bookkeeping on the embedding. A whole fermion generation, quarks and leptons together, collapses into a handful of irreducible representations. In SU5, these are the 5 bar plus the 10. In SO10, they are a single spinor, the 16. Every problem in the chapter is the same move. Read off what the embedding forces, which massive gauge bosons appear, which baryon number violating operators they permit, and how the SO2N spinors are constructed. The surprise that does the work is this. Seating a quark beside a lepton in one multiplet makes the proton mortal. This section explains grand unification as a single structural move. Read the standard model's inventory as debris, 3 gauge groups, a litter of fermion multiplets, quarks over here, leptons over there, hypercharges assigned by hand. Grand unification reads that debris backwards. The move is to embed the 3 gauge groups, SU3 cross, SU2 cross U1 inside one simple group, SU5. Once embedded, the scattered fragments become branches of a single irreducible representation restricted to the subgroup. A generation is the 5 bar plus the 10. Nothing is chosen. The whole chapter is that one move. Take a representation of the big group, restrict it, and it splits into exactly the pieces you had been calling separate particles, charge quantization and coupling unification. Stop being hypotheses. They become consequences of the splitting. An adjoint Higgs, the 24, then selects which fragmentation the vacuum actually realizes. This section explains how a particle can be a feature of the vacuum's own shape rather than something placed into it. A particle need not be something added to the vacuum. It can be a knot. The vacuum cannot untie. Each problem here builds one such configuration: the Sine-Gordon kink, the planar vortex, the monopole. What holds them together is topological, the way the field wraps the vacuum's degenerate values at spatial infinity, rather than any stored eps the vacuum's degenerate values at spatial infinity, rather than any stored energy. That winding is an integer. No smooth local motion can change it, so the object is stable, and its flux arrives in quantized units for free. The chapter's single move, topology at the boundary, is the conserved charge. The monopole closes it. Even the angular momentum stored in the field of an electric charge, E, and a magnetic charge, G, the piece pointing along minus Eg times the radial unit vector r hat, is bookkeeping the winding O's. This section explains a conserved charge that no symmetry generates, which is the spine of the whole chapter. Start with the smallest anchor, the Sine-Gordon kink. A field pinned to two distinct degenerate vacua at x equals plus and minus infinity cannot be deformed to the trivial configuration without crossing infinite energy. So the integer counting how many vacua it spans is conserved by topology, not by Noether. The magnetic monopole is that identical move promoted to 3 dimensions with a gauge group. The field on the sphere at infinity wraps the vacuum manifold, and the wrapping number is magnetic charge. Dirac's quantization condition stops being a quantum accident and becomes the flat statement that a winding number must be an integer. This section explains the instanton, the structural primitive, at layer 1. Wick, rotate to imaginary time, and a tunneling problem turns classical. The particle that could never cross the barrier now rolls freely across the inverted potential, and that finite action trajectory joining 2 vacua is the instanton. The chapter's whole leverage is one saddle point move. The Euclidean path integral is dominated by classical solutions, and the leading one carries a weight of e raised to minus s naught divided by h bar. The surprise that does the work lives in the action. C naught is proportional to 1 over g squared, non-analytic in the coupling, so no order of perturbation theory can ever reach it. That is what the apparatus is for. Instantons are how you compute the physics perturbation theory is structurally blind to degenerate vacua talking to each other underneath the series. This section explains why some physics can never appear in perturbation theory, and how imaginary time recovers it. Perturbation theory is a power series in h bar, but a tunneling amplitude scales as e to the minus s over h bar, which is non-analytic at h bar equals 0, so no order of the series can ever see it. The escape is imaginary time. Rotate t to minus I tau, and the oscillatory path integral becomes damped, now dominated by a genuine classical solution of the theory with its potential flipped upside down. Tunneling through a barrier becomes a particle rolling between 2 hilltops, the degenerate vacua. That finite action, Euclidean trajectory, is the instanton. Here, x equals a times the hyperbolic tangent of omega times tau minus tau naught, all over 2, localized in tau, joining plus a and minus a. Its action fixes the tunneling rate, and hence the vacuum level. The chapter's one move, non-perturbative physics, is the classical physics of the Euclidean theory.